Hello friends, you are watching Civil Engineering Infrastructure. This channel we understand road construction, pavement engineering, laboratory testing and practical civil engineering concepts in detail. Today's lecture we are going to understand a very interesting research topic in detail. Optimization of aggregate particle packing for improved interfacial bonding in wrap-based concrete mixtures. Now the name may seem a bit long, but we will understand it step by step in very simple language. First of all, let us understand what this topic actually says. Here we are talking about reclaimed asphalt pavement, i.e. wrap. When old asphalt roads are removed, that material is not wasted but is recycled and used again. Now the biggest problem here is bonding. When we use wrap aggregates in concrete, there is a bitumen coating on their surface. This coating does not allow strong bonding to form between the cement paste and aggregates. Due to this, the strength and performance of wrap-based concrete is affected. So in this lecture we will understand whether if we optimize the particle packing of aggregates, then can we improve this bonding problem or not. This entire lecture, we will understand step by step. What is wrap material? Its behavior, how is it? What is particle packing? What is the CPM model? Laboratory testing done. And most importantly, what do the actual research results say? This lecture will not be just theoretical. In this you will get practical engineering understanding, research level clarity and microstructural behavior. You will get a deep explanation of this. If you are a civil engineering student, site engineer or preparing for competitive exams, then this lecture is going to be very useful for you. Presented by Civil Engineering Infrastructure. Introduction to wrap. Now in this slide we understand reclaimed asphalt pavement, i.e. wrap in detail. Reclaimed asphalt pavement is a recycled material obtained by removing and processing existing asphalt pavement. This means that when old asphalt roads are removed, that material is not wasted but is recovered and used again. This process we can reuse old material in new pavement construction. Now if we talk about the composition of wrap, then there are mainly three things inside the wrap material: aggregates, aged bitumen binder, and mineral filler. These three together form the structure of wrap material. Now there are some important benefits of using wrap. The first advantage is that recycling asphalt reduces construction costs, because we need less new raw materials. Secondly, it helps in saving natural resources. And third, wrap supports sustainable and environmentally friendly construction. Meaning, if seen overall, wrap is a material which is cost-effective and also beneficial for the environment. Now the main idea of the engineer's note given here is that proper processing and correct mix design are very important while using wrap material. If the processing and mix design is not done correctly, the strength and durability of the pavement layers can be affected. Therefore, while using wrap, it is not enough to just reuse the material, but it is equally important to design it properly. Need for asphalt pavement recycling. Now in this slide we understand why asphalt pavement recycling is needed. In today's time, the development of road infrastructure is increasing very rapidly. Due to this, the demand for aggregates and bitumen is also continuously increasing. But if we dispose of old pavement materials as waste, it creates both environmental and economic problems. Now if we look at the practical scenario, A large amount of old asphalt pavement is generated during road rehabilitation. This means that when roads are repaired or reconstructed, a lot of old material is removed. Now here comes a big problem of disposal. If this asphalt waste is not managed properly, it can cause environmental pollution. This is where RAP recycling comes into play. When we recycle RAP, it reduces material cost and also conserves natural resources. Meaning we can reduce the dependency on new aggregates and bitumen. So overall, asphalt pavement recycling is not just an option, but has become a necessity. Now the main idea of the engineer's note given here is that recycling asphalt pavement is one of the most effective sustainable practices in modern highway engineering. Meaning, if we want to do sustainable construction, then it is very important to adopt recycling approach. If this concept is becoming clear to you till here, and you want to learn similar practical civil engineering topics, so please subscribe to the channel. And don't forget to press the bell icon. The notification of upcoming lectures first. Composition of RAP material. Now in this slide we understand the composition of RAP material in detail. Reclaimed asphalt pavement i.e. RAP is mainly made of aggregates whose surface has a coating of aged bitumen binder. This material is recovered from existing asphalt pavement layers. If we understand the components of RAP, then the first thing that comes in it is COARAC and fine aggregates. This means that both types of aggregates are present in RAP, which define the structure and strength of the material. The second component is AGED bitumen binder. It is present as a coating on the surface of binder aggregates. But it is important to note that this bitumen is aged, whose properties are different from fresh bitumen. The third component is mineral filler. This is also present in recycled material, which will affect the overall behavior of the mixture influences. So if we look overall, RAP is not a simple material. IT is a combination of aggregates plus aged bitumen plus filler. And this combination is its behavior makes it complex. Now the main idea of the engineer's note given here is this. It is very important to understand the composition of RAP. Effective recycled pavement mixture is designed on this basis. If the composition is not understood correctly, so mix design will also not be correct. RAP collection process. In this slide we understand the collection process of RAP material. Reclaimed asphalt pavement i.e. RAP is mainly obtained during the rehabilitation or reconstruction of existing asphalt roads. Meaning, when old roads are repaired or reconstructed, RAP material comes up. An important role in this process is played by OAF milling machines. Special milling machines remove the asphalt surface and simultaneously collect the material so it can be used for recycling. Now let us understand this process step by step. First of all, milling machines remove damaged asphalt surfaces. Meaning, the surface which has been damaged is carefully cut and removed. After this, COLLECTED material is transported to recycling plants, where this material is further processed. And then, RECLAIMED material is stored as a RAP stockpile. Can be used in further processing and mix design. So overall, RAP collection is a systematic process which includes all three stages: removal, transportation and storage. Now the main idea of the engineer's note given here is this. If the milling and collection process is efficient, so the quality of recycled pavement mixtures will also be better. This means that the collection stage itself indirectly affects the final performance. Have understood the entire process of RAP step by step till now. So do one thing. Subscribe to the channel and don't forget to press the bell icon. Because in future we are going to understand even more deep engineering concepts in this simple language. Processing of reclaimed asphalt pavement. In this slide we understand the processing stage of RAP material. After collection, RAP material is not used directly. Rather, it is processed so that it becomes suitable for pavement construction. This processing mainly involves crushing, screening and sometimes reheating. First of all, RAP material is crushed, meaning large chunks are converted into smaller aggregate sizes, so that it can be suitable for mix design. After this, screening process is done. In this, particles are separated according to their size, so that correct gradation can be achieved. Some cases, reheating of RAP material is also done. Can mix well with new materials. And finally, processed RAP is reused in asphalt or concrete mixtures, meaning this material becomes ready for use again in the construction process. So overall, the processing stage directly influences the quality of RAP material. Now the main idea of the engineer's note given here is this. Proper processing improves the quality of RAP material and improves the performance of recycled pavement mixtures. Meaning if the processing is correct, then the final output will also be good. Introduction to particle packing. Now in this slide we understand the concept of particle packing, which is the core concept of this entire lecture. Particle packing means the arrangement of particles, in which they are arranged in such a way that maximum density is achieved inside the mixture and voids remain minimum. Meaning in simple language, arranging particles in such a way that there is minimal empty space. Proper particle packing is very important in concrete and pavement materials, because it directly improves strength and durability. Now let us understand this concept step by step. First of all, ARG particles form the primary structure of the mixture, meaning large particles framework is prepared. After this, SMALLER particles fill the empty space between larger particles, due to which voids are reduced and the mixture becomes dense. When we optimize this packing, SO density increases and mechanical performance improves, meaning both strength and durability are better. So overall, particle packing is a very powerful concept, which can significantly improve the performance of the mixture. Now the main idea of the engineer's note given here is this. Optimizing particle packing is an effective way to improve interfacial bonding between aggregates and cement paste, especially in RAP-based concrete. This means that this concept will help us in solving our main problem, bonding. If now this concept is becoming clear to you that how important is particle packing, so please like the video. And don't forget to subscribe the channel and press the bell icon. Because further we are going to understand this concept at an even deeper level. Problem with RAP-based concrete. In this slide we understand the main problems of RAP-based concrete. Although RAP is a durable construction material, but when it is used in concrete mixtures. So some challenges arise. The main reasons for these challenges are AGED bitumen coating on the surface of RAP aggregates. Now let us understand this problem step by step. The very first problem. Bitumen coating reduces the bonding between aggregates and cement paste. This means that the strong bond that should be formed does not develop properly. Second important problem. WEAK interfacial transition zone. It is the zone where aggregate and cement paste meet. If this zone is weak, the strength of the concrete will directly reduce. Third problem. HIGHER RAP content may reduce mechanical performance. Meaning if we increase the percentage of RAP more, so there is a negative effect on strength, durability and overall performance. So overall, the use of RAP is beneficial. The problem of bonding and strength is also associated with it. Now the main idea of the engineer's note given here is this. The biggest challenge of this technology is to improve the bonding between RAP aggregates and cement paste. Meaning the focus of the entire research is on solving this problem. Research gap. Now in this slide we understand the research gap, which is the most important foundation of this entire study. Till now many researchers have worked on using RAP aggregates in concrete. Major challenges still remain, especially related to bonding and mechanical performance. Meaning research has been done, but the problem has not been completely solved. Now let us understand this a little deeper. When we use RAP aggregates in concrete, the first problem that arises is POR particle packing. If the particles are not arranged correctly, so the voids inside the mixture increase. Now try imagining. If there is more space between aggregates, so the cement paste will not be able to fill those voids completely. And where the voids remain, weakness will develop there. Let us understand this with a simple example. Suppose you put only big stones in a container. So there will be a lot of empty space between them. Put smaller particles between them, so that empty space gets filled. THIS is the concept of particle packing. If the packing is poor, there will be more voids. If packing is optimized, there will be less voids. Comes the second major problem. WEAK bonding between RAP aggregates and cement paste. As we saw earlier, RAP aggregates have a bitumen coating on their surface. This coating does not allow the cement paste to attach directly, meaning the bond remains weak. Now if the bond weakens, so load transfer will also not be proper, and ultimately the strength of the concrete will decrease. Now the third important point. LIMITED research on optimizing particle packing. To date, most studies have focused on using RAP. But there has been very limited research on optimizing particle packing. Meaning, THE problem is known, but its proper solution was not explored. This is where this research becomes important. This study specifically focuses on BY optimizing particle packing, IMPROVING bonding and performance. Now the image shown on the right side. She is also showing the same concept. Poor packing on one side, where there are more voids. And on the other side is optimized packing, where the particles are filled well. THIS is visual proof that improving packing makes the structure denser. Now the main idea of the engineer's note given here is this. If we optimize particle packing, so we can reduce the voids and can significantly improve the strength and durability of wrap-based concrete. Now let's understand a practical thing. If there are more voids in the concrete at the site, so what will happen? Strength will decrease. Water will enter. Durability will be lower. Cracks will appear soon. But if the packing is proper, will be dense, bonding will be better, strength will improve. So overall the main takeaway from this slide is this. Problem is clear, poor packing plus weak bonding. The research gap is clear, little work has been done on packing optimization. The solution direction is clear, optimize particle packing. If you now understand where the research was missing and what new learning we are going to do, so definitely watch this video continue. And don't forget to subscribe to the channel and press the bell icon. Because now we are going to move towards the actual solution. Research objective. Now in this slide we understand the objective of this entire research. Meaning by now we have understood the problem. Now we will understand what is the goal of this research. The main objective of this research is improving the performance of wrap-based concrete. But how? By optimizing the particle packing of aggregates to improve bonding, and internal voids should be reduced. Now let us understand it in step-by-step detail. The first objective, improve interfacial bonding between wrap aggregates and cement paste. As we saw earlier, wrap aggregates have a bitumen coating on their surface. This coating makes the bonding weak. Now if the bonding is weak, so load transfer will also not be proper. Now imagine, when the load comes on the concrete, so it gets transferred from aggregate to cement paste and then to another aggregate. If the bonding in between is weak, so the load transfer will break. THIS is the beginning of failure. Focus of this research is strengthening bonding. Now the second objective, optimized particle packing to reduce internal voids. As we saw in the previous slide, if the packing is poor, there will be more voids. Now what does voids mean? Empty space and empty spaces in concrete weakness. A simple example. If you built a wall of bricks and left gaps between them, so that wall will be weak. But if the gaps are filled properly, then that structure will become strong. The same concept applies here as well. When particle packing is optimized, voids are reduced, density increases, the structure is compact. Now the third objective, enhance mechanical strength and durability. Meaning what is the final goal? Making concrete stronger and more durable. Understand an important thing here. Strength and durability directly depend on bonding, on packing, on voids. THESE3 improve. So the overall performance automatically improves. Now the image shown on the right side. It represents optimized particle packing, where creating large aggregates structures. Smaller aggregates are filling the voids. RESULT dense and strong structure. Now the main idea of the engineer's note given here is this. Optimizing aggregate particle packing plays a very crucial role. Increasing density, to improve strength and in enhancing overall performance. Understand this from a practical point of view. If you are pouring concrete on the site and it does not have proper packing, so what will happen? Honeycombing will come. Voids will remain. Strength will decrease. Durability will deteriorate. But if the packing is optimized, the structure will be compact. Bonding will be better. Lifespan will increase. So the final takeaway from this slide is this. The objective is clear: to improve performance. APPROACH is clear: optimize particle packing to do. TARGET is clear: bonding improve plus voids reduce plus strength increase. If it is now clear to you what exactly this research wants to achieve, so the next part is going to be even more interesting for you. So definitely watch the video continue. And don't forget to subscribe to the channel and press the bell icon. Because now we are going to move towards methodology and actual implementation. Research methodology overview. In this slide we understand the methodology of the entire research. Meaning till now we have understood the problem and objective. Now we will see what approach researchers adopted to solve this problem. The main focus of this research methodology is IMPROVING, the performance of wrap-based concrete. And this improvement is achieved. THROUGH, optimized particle packing. AND through systematic experimental investigation. Now here is a very important word. SYSTEMATIC. Meaning this research has not been done randomly. Rather, a proper step-by-step scientific process has been followed. Let us understand this entire methodology step by step. Step 1. Selection and characterization of materials. The very first step is SELECTION and characterization of wrap aggregates and other materials. Meaning, which wrap will be used? What are its properties? What is the size, shape, texture of the aggregates? Now what does characterization mean here? STUDYING, the properties of the material in detail. As specific gravity, gradation, surface texture. If you don't understand the material properly in the beginning, mix design ahead may go wrong. THEREFORE, this step is very critical. Step 2. Particle packing optimization. Now comes the second step. OPTIMIZING, particle packing, is the core part of this entire research. Analytical models are used here, like CPM, compressible packing model, so that the aggregates are arranged such that voids should be minimum, density should be maximum. Now imagine particles of different sizes. If you put them randomly, there will be more voids. But if you arrange them scientifically, smaller particles will fill the space between larger particles. THIS is what optimization is. Step 3. Concrete mix preparation. Now comes the third step. PREPARATION of concrete mixtures. Meaning mix design is made on the basis of optimized packing. Here attention is paid to correct proportion, water-cement ratio, wrap content. Now this is very important because if the mix design is not correct, then the entire optimization will be wasted. Step 4. Laboratory testing and performance evaluation. Now comes the final step. Laboratory testing and performance evaluation. Meaning the concrete that has been made, its actual performance is checked. Here tests are performed such as compressive strength, flexural strength, durability tests. Understand a very important thing here. A theory is valid only if it is supported by practical results. Therefore, the testing stage is the most critical. RIGHT side flow diagram explanation. Now the diagram given on the right side. He is showing the entire methodology visually. 1. Material selection. 2. Particle packing optimization. 3. Concrete mix preparation. 4. Performance evaluation. ITS a complete flow, from the beginning to the final result. Now the main idea of the engineer's note given here is this. Systematic experimental methodology ensures that to enable accurate evaluation of the performance of wrap-based concrete mixtures, meaning if the process is proper, then the result will also be reliable. Practical understanding. Now let's understand this at the site level. If you are making concrete without planning, material not checked, mix design is random, not tested, the result will be unreliable. But if you follow the proper methodology, correct material selection, proper design, testing, so the quality will be assured. Final takeaway. RESEARCH is not random, it is systematic. Every step has its own importance. Final performance depends on the entire process. Materials used in the study. Now in this slide we understand the materials that have been used in this entire research. Materials play a very important role in any experimental study, because the final result completely depends on which material you have used and what are its properties. In this research, for experimental investigation of wrap-based concrete, many construction materials have been used. These primarily include RECYCLED aggregates, A&D conventional concrete ingredients. Now let us understand these materials one by one in detail. 1. Reclaimed asphalt pavement wrap aggregates. The first and most important material is RAP aggregates. These are obtained from recycled asphalt roads. Now, here's an important thing to understand. RAP aggregates are different from normal aggregates. Why? Because their surface has an aged bitumen coating. This coating is the problem of this entire research. And focus 2. Now think practically. If the surface of the aggregate is smooth or coated, so the cement paste will not attach properly on it. THIS is the root cause of the bonding problem. Therefore, it is very important to understand and characterize wrap aggregates. Though natural aggregates. Now here's the second material. NATURAL aggregates. These are used in the mix so that proper gradation can be maintained. Now what does graduation mean? CORRECT proportion of aggregates of different sizes. If the gradation is not proper, there will be more voids. The packing will be damaged. Strength will decrease. Therefore, the role of natural aggregates is CREATING balance with wrap aggregates. 3. Ordinary Portland cement OPC. Now here is the third material. ORDINARY Portland cement. This is the binding material of concrete. The main function of cement? Binding aggregates. When cement reacts with water, hydration. So a paste is formed which joins the aggregates to form a solid structure. But here comes the same problem. If the surface of the aggregate is coated, as in wrap, then the bonding will become weak. Char. Water. Now here's the next material. Water. The role of water is very critical. It reacts with the cement and initiates the hydration process. If the water is not in the right quantity, will decrease hydration incomplete. Will be more, strength will be less. THEREFORE, water-cement ratio is a very important parameter. Right side image explanation. Now the image given on the right side, visually showing all these materials. Wrap aggregates, natural aggregates, cement, water. This image gives us a clear idea that what are the basic components of concrete mix. Engineer's note explanation. Now the main idea of the engineer's note given here is this. Proper selection and characterization of materials is very important, so that reliable experimental results can be obtained. Meaning, if you did not choose the material correctly, or did not understand its properties, so the result of the entire research may be wrong. Practical understanding. Now let's understand this at the site level. If you are on a construction site, use poor quality aggregates. The cement is not correct. No water control. So the concrete may fail. But if the materials are right, performance will be reliable. Strength will come properly. Durability will improve. Final takeaway. If concrete quality of materials. RAP aggregates are a special case due to the bitumen coating. PROPER selection and characterization is mandatory. Properties of wrap aggregates. Now in this slide we understand the properties of wrap aggregates in detail. This is a very important slide because this is where we understand why wrap aggregates behave differently from normal aggregates. The physical and mechanical properties of reclaimed asphalt pavement aggregates are unique. And the main reason for this is aged bitumen coating present on their surface. Now let us understand this in detail. Bitumen coating effect. First of all, RAP aggregates have a coating of residual bitumen binder on their surface. This coating comes from asphalt pavement, which remains on the aggregates even after recycling. What does this coating do? THIS changes the surface of the aggregate. Normal aggregates have a rough surface, due to which the cement paste gets attached well. But in wrap aggregates, BECOME is coated and comparatively smooth. Its direct effect, bonding becomes weak. PHYSICL properties difference. Now the second important thing. If wrap aggregates are different from natural aggregates. These include DNSITY, GRADUATIOing, WATER absorption. DNSITY of wrap aggregates can generally be lower than natural aggregates. Why? BECAUSE bitumen coating is lightweight. GRADUATIOing. Gradation may also vary as wrap material is already processed and crushed. WATER absorption. Water absorption behavior of RAP aggregates, it is also different. Bitumen coating affects water penetration. What does it mean? ADZUSTMENTs have to be made in the mix design. NEED for proper characterization. Now a very important point. PROPER characterization of RAP aggregates is essential before using them. Meaning, their properties will have to be measured. Behavior have to understand. If you use it without characterization, so the mix design can be wrong. A&D performance may deteriorate. RIGHT side image explanation. Now the image shown on the right side. She is showing off these properties visually. Gradation, sieve analysis. Density measurement. Bitumen coating. This image gives us an understanding of the practical lab setup. ENGINERS note explanation. Now the main idea of the engineer's note given here is this. It is very important to understand RAP aggregate properties, so that optimized and durable recycled concrete mixtures can be designed. Meaning, RIGHT design right understanding of properties. PRACTICAL understanding. Understand this from both site and lab perspective. If you are using RAP aggregates and don't know their properties, water demand will be wrong. Bonding issue will remain. Strength will be unpredictable. But if the properties are properly known, mix design will be accurate, performance will be predictable, durability will improve. Final takeaway. RAP aggregates do not behave like normal aggregates. Bitumen coating behavior changes. The PROPER characterization is mandatory. Particle packing theory. In this slide we understand the particle packing theory in detail. This concept is the backbone of this entire research, because this is where we understand how to arrange aggregates so that maximum performance can be achieved. Particle packing theory basically states that THE particles should be arranged in the mixture in such a way that maximum density is achieved and have minimum void spaces. Now there are two important terms here. MAXIMUM density. MINIMUM voids. Maximum density, what does it mean? Maximum density means MAKING the structure as compact as possible. Now imagine. Just put big rocks in a container. So there is a lot of empty space between them. Put smaller particles between them, so that space gets filled. RESULT the structure becomes more dense. MINIMUM voids, what does it mean? Voids means EMPTY space. If there are more voids in concrete, strength will decrease. Water will enter. Durability will decrease. But if there are fewer voids, the structure will be stronger. Durability will increase. Performance will improve. Understand the theory step by step. Us understand this theory through bullet points. ARGR particles, structural skeleton. What do large particles do? THIS forms the basic structure of the mixture. Meaning, just like a building has columns and beams, similarly, large aggregates form a framework. SMALLER particles, void filling. Now comes the role of smaller particles. IT fills the empty spaces between the larger particles. This is a very important step because THIS is where the voids are reduced. Now imagine, if there are no small particles, so there will be empty space between the big particles. OPTIMIZEDD packing, final result. When large and small particles are properly combined, THEN optimized packing is achieved. Result: density increases. Internal porosity is reduced. Mechanical performance improves. Right side image explanation. Now the image shown on the right side. She is clearly showing optimized particle packing. In this you can see large particles, orange, forming structure. Medium and small particles filling the voids. IS an ideal packing condition. ENGINERS note explanation. Now the main idea of the engineer's note given here is this. Efficient particle packing strength, durability of concrete, and significantly improves bonding characteristics. Meaning, THE better the packing. THE better the performance of the concrete. PRACTICAL understanding. Now let's understand this at the site level. If aggregates in the concrete were added randomly, there will be more voids. Will honeycomb. Strength will decrease. But if the packing is optimized, will be dense. Bonding will be strong. There will be fewer cracks. FINAL takeaway. PARTICAL packing arrangement science. GOAL maximum density plus minimum voids. RESULT better strength plus durability plus performance. Importance of packing density. Now in this slide we understand the importance of packing density in detail. This concept is very crucial because it directly decides whether the concrete will be strong or weak. Packing density means CLOY packed the aggregates are in the mixture. If the packing density is high, THE particles will be closer to each other. THERE will be fewer voids. And if the packing density is low, THE gaps between particles will be larger. THERE will be more voids. High packing density, what is the benefit? Now first of all let us understand the effect of high packing density. HIGHER packing density leads to fewer voids. Meaning, when the particles are well packed, so there is very little empty space between them. Now what is its direct benefit? MECHNICL properties improve. Meaning, compressive strength increases. Durability improves. Permeability is low. Low packing density, what problem? Now on the other side. LOW packing density. What happens here? There are more voids. Cement paste has to be filled more. Weak zones develop. Now imagine two containers. In one the particles are loosely placed, more voids. In the second are tightly packed, less voids. Which one will be stronger? OBVIOUSLY tightly packed one. BULLET points explanation. Now let us understand the points of the slide one by one. HIGHER packing density reduces internal void spaces. Meaning, THE better the packing, the better. THE less free space there will be. REDUCED voids improve strength and durability. This is a very important relation. VOIDS strength. Now understand the practical reason. Where there will be void, that's where the crack will initiate. OPTIMIZEDD particle packing enhances performance. Meaning, if packing is optimized, so the entire concrete will perform better. Right side image explanation. Now the comparison image on the right side. She explains the concept very clearly. AEFT side, low packing density. More voids. Gaps are shown in red. RIGHT side, high packing density. Particles closely packed. Very few voids. THIS difference changes the entire performance. Now the main idea of the engineer's note given here is this. To improve packing density. A method to increase the structural efficiency of aggregate-based materials. The most effective way. Meaning, if the packing is correct, so the entire structure will be efficient. PRACTICAL understanding. Now let's understand this at the site level. If the concrete is poorly packed, honeycombing will come. Voids will remain. Strength will decrease. But if the packing is good, will be dense. Bonding will be strong. Durability will increase. FINAL takeaway. PACKING density performance controller. HIGH density low voids high strength. LOW density high voids weak concrete. If it is now clear to you how powerful a concept packing density is, miss the upcoming slides. Because now we are going to understand its practical implementation and models in more depth. Want to watch such deep civil engineering lectures regularly? So subscribe to the channel and don't forget to press the bell icon. Compressible Packing Model, CPM. Now in this slide we are going to understand a very important concept. Compressible Packing Model, CPM. This model is used to scientifically understand and predict particle packing. Till now we have understood the concept that packing is important. But now comes the question. TO measure packing. OPTIMIZD. This is where the CPM model comes into play. WHAT is CPM. Compressible Packing Model is an analytical model which predicts the packing density of granular materials. Meaning, particles of different sizes. So this model can tell how to arrange them so that maximum packing density can be achieved. Particle interactions, most important concept. Comes a very important point. Particle interactions. Meaning, when particles of different sizes are together, influence each other. Now imagine, there is a large particle. There are small particles around it. Now the smaller particles, WILL fill around the larger particle. THEY will also interfere in some places. That is, particles don't just fill. Rather they also interact. CPM considers this interaction. Compaction effect. Now the second concept. COMPACTION. When external force is applied, such as vibration, compaction. So the particles become more closely packed. The CPM model also considers that HOW will the packing density change after compaction. Meaning, THEORETICAL packing plus practical compaction final packing. BULLET points explanation. Now let us understand the points of the slide in detail. CPM predicts packing density of mixed aggregates. Meaning, THIS model predicts the packing density of mixed size aggregates. This is very useful because in real concrete, we always use different sizes. IT considers interaction between different particle sizes. Meaning, just the size, but the interaction of the particles is also important. SMALL particles don't always fit perfectly. SOMTIMES they also create disturbance. CPM includes all these effects. HELP in designing optimized aggregate gradation. Meaning, with the help of this model we can design ideal gradation. I.E. WHICH size should be in what percentage? So that voids should be minimum. Density should be maximum. Right side image explanation. Now the image on the right side. She is visually demonstrating the CPM concept. DIFFERENT size particles, large, medium, small, fine. COMPRESSIBLE forces are acting from above. Result: THE particles are becoming more closely packed. SEHIV maximum packing density it is happening. Now the main idea of the engineer's note given here is this. The CPM model provides a theoretical approach. Thereby, aggregate packing efficiency can be improved. In wrap-based concrete. Meaning, THI's model guides us scientifically. How to achieve the best packing. PRACTICAL understanding. Now let's understand this in a practical way. If you are doing a mixed design without a model, there will be trial and error. It will take more time. The result will be inconsistent. But if you use CPM, optimized design will be available. There will be fewer voids. Performance will be better. Final takeaway. CPM scientific tool for packing optimization. IT considers both particle interaction plus compaction. THIS helps in designing optimal gradation. Taguchi optimization method. Now in this slide we are going to understand another very important concept. TSUCHI optimization method. This method is mainly used to optimize process parameters so that we can achieve the best result in fewer experiments. Comes a basic question. WHEN we have so many variables like particle size, proportion, water content. So how do we find the best combination? If we test every possible combination, so it will take a lot of time. The cost will increase. There will be too many experiments. THIS is the problem that the Taguchi method solves. WHAT is Taguchi method. Taguchi method is a statistical approach which helps in finding the optimal solution in a limited number of experiments. Meaning, AES is experiments best result. Orthogonal array core concept. Important part of this method. ORTHOGONAL array is a structured table in which different combinations are arranged systematically. Now imagine you have 10 factors. Factor A particle size. Factor B percentage. Factor C water content. If each factor has 2-3 levels, so the total combinations can be very high. But what does the Taguchi method do? TEST only selected combinations. BUT selects in such a way that maximum information is available. THIS is the efficiency of this method. Identifying optimal combination. Now the next step is find the optimal combination to do. After doing the experiments, the Taguchi method analysis does that. WHICH combination is giving the best performance? Meaning, which particle size is best? Which proportion is correct? Which mix is performing best? Variability reduction. Now another important advantage. THI's method reduces variability. Meaning, I is consistent. Now let's understand the practical aspect. If the mix design is unstable, so the strength can change every time. But if the optimization is correct, WILL be repeatable. PERFORMANCE will be reliable. BULLET points explanation. Now let us understand the points of the slide in detail. USES orthogonal arrays to design experiments efficiently. Meaning, EXPERIMENTS don't happen randomly. RATHER, they happen in a planned manner. HELPs identify optimal combination of parameters. Meaning, BEST mix design find helps too. REDUCES variability and improves performance. Meaning, CONSISTENCY improves. THE final output is reliable. Right side image explanation. Now the diagram on the right side. He's showing the entire Taguchi process. FACTORS A, B, C, and their levels. COMBINATIONS in orthogonal array. SOME selected tests, test 1, test 2, test 3. AND then the optimization result. THI's complete flow shows how to get the best result in fewer experiments. ENGINERS note explanation. Now the main idea of the engineer's note given here is this. Taguchi optimization technique for wrap-based concrete helps determine the most efficient particle packing configuration. Meaning, THI's method directly helps us in solving our main problem. THAT is finding the best packing combination. PRACTICAL understanding. Now let's understand this in a practical way. If you reworking without the Taguchi method, there will be more trial and error. It will be a waste of time. The cost will increase. But if you use Taguchi, you will get results in fewer experiments. Optimized mix design will be available. Performance will be better. Final takeaway. TAGUCHI smart experimentation technique. BEST result in less experiments. FIND the optimal mix design a powerful tool too. Experimental mix design. Now in this slide we understand the experimental mix design in detail. This stage is very critical because it is here that the theory practically converts. So far we have understand the materials. Particle packing concept explained. Also understood CPM model and Taguchi method. Now comes the question. APPLY all this to the actual concrete mix. THIS is where mix design comes in. Is mix design? Mix design means determining the correct proportion of different materials so that get optimized particle packing and mechanical performance improves. Meaning in simple language, WHICH material to put in how much. OBJCTIV of mix design. The main goal of mix design in this research is OPTIMIZING particle packing. AND improving strength. Now let us understand it step by step. Step 1. Selection of wrap and natural aggregates. The very first step is ACLECTION of RAP aggregates and natural aggregates. Now balance is very important here. Why? RAP aggregates weaken bonding. BUT natural aggregates improve strength. So, COMBINATION of both is essential. Now imagine, if you use 100% RAP, bonding will be weak. Strength will decrease. But if the mix is balanced, PERFORMANCE may improve. Step 2. Determination of optimal particle size distribution. Now the second step. DETRMINE the optimal particle size distribution gradation to do. This is where the CPM model and Taguchi method come in handy. Meaning, WH80 should be the particle size. If the gradation is incorrect, voids will increase. The packing will be damaged. But if the gradation is optimized, PACKING will be best. Step 3. Preparation of concrete mixes. Now the third step. PREPARING different concrete mixes. Meaning, DIFFERENT combinations are made. As different RAP percentage, different gradation, different mix proportions. Then all these mixes are tested. WHY multiple mixes. Now here is an important question. WHY not make the same mix? Because WE have to find the best combination. So, MULTIPLE trials are conducted. A and D then the comparison is done. Right side image explanation. Now the image on the right side. She is showing the actual concrete mixing process. You can see aggregates, cement, mixing process. THIS is a real process that takes place either in the lab or on-site. Now the main idea of the engineer's note given here is this. Careful mix design is very important, so that desired strength and durability can be achieved. Meaning, if the mix design is not correct, THEN the entire concrete may fail. PRACTICAL understanding. Now let's understand this at the site level. If the mix design is random, strength will be inconsistent, durability will deteriorate, cracks will appear soon. But if the mix design is optimized, performance will be predictable, strength will be reliable, will be long-lasting. Final takeaway. MIX design theory plus practical implementation. CORRECT proportion better packing plus better strength. MULTIPLE trials best result. Preparation of concrete specimen. In this slide we understand the preparation of concrete specimens in detail. This stage is very critical because it is here that samples are prepared for actual testing. So far we have made a mix design. Optimal combination decided. Now the next step is CONVERTING that mix into actual specimens, so that their strength and performance can be tested. WHY specimen preparation is important. First, let's understand this. WHY is specimen preparation important? Because if the specimen is not prepared properly, so the testing results may be wrong. Meaning, WRONG preparation wrong conclusion. Therefore, this step is done very carefully. Step 1. Placing concrete in molds. The very first step. POURING the concrete mixture into the molds. Cube molds are used here, e.g. 150 mm, 150 mm, 150 mm. Now, something to note. Concrete is poured in layers. Why? To ensure proper compaction. And reduce air voids. Step though compaction. Now the second and very important step. Proper compaction. Compaction means removing entrapped air from concrete. Now imagine, if air bubbles remain inside, voids will form, strength will decrease. Therefore compaction is done by manual tamping or from a vibration table. IT's goal is maximum density achieved to do. Step 3, demolding and curing. Now the third step. Demolding the specimens. This is usually done after 24 hours. After this, the curing process begins. Meaning of curing. Providing proper moisture and temperature to the concrete, so that the hydration process continues. If curing is not correct, strength will not develop. Cracks may occur. Therefore curing is very critical. Right side image explanation. Now the image on the right side. She is showing the actual specimen preparation. You can see cube molds, concrete filling, manual work. THIS is a common process in both the lab and on-site. Now the main idea of the engineer's note given here is this. Ensure proper specimen preparation does that. Of laboratory testing should be accurate and reliable. Meaning, RIGHT preparation right result. PRACTICAL understanding. Now let's understand this in a practical way. If in the specimen, the compaction is not correct, air voids remained, curing is bad, THEN the testing result will be wrong. But if everything is correct, the result will be accurate, the comparison will be correct, will be reliable. FINAL takeaway. SPCIMEN preparation foundation of testing. COMPACTION plus curing strength development. PROPER method reliable results. Laboratory testing procedures. Now we have reached the most important phase, laboratory testing. So far we have wrap material understood, mix designed, specimens prepared. Now the next step is testing their actual performance. WHAT is laboratory testing. Laboratory testing means evaluating the properties of concrete specimens in a controlled environment. Here we check strength, density, bonding behavior. THAT is the theoretical design now goes into practical validation. TEST compressive strength test. Most important test. COMPRESSIV strength test. This test, THE concrete specimen is placed in a compression machine. Then, THE load is applied gradually until the specimen fails. THE load at which failure occurs. It is called compressive strength. WHY important? The primary property of concrete is strength. Structural safety depends on this. If the strength of wrap-based concrete is low, then its use will be limited. TEST though density evaluation. Now the second parameter. DNSITY. Density explains HOW compact and dense the concrete is. If the density is low, There are many voids. Strength will decrease. If the density is high, packing is good. Performance will be better. HENCE, the density is directly related to the packing efficiency. Test 3 Bonding Analysis. Now the most critical concept. Bonding between wrap aggregates and cement matrix. This is where the biggest problem arises in wrap concrete. Why? AGED bitumen coating is applied on wrap aggregates. THIS coating reduces bonding with the cement paste. Therefore, testing checks. Interfacial bonding. Its strength. Microstructure behavior. If the bonding is weak, cracks will appear soon. Durability will be lower. Right side image explanation. Now the image on the right side. THIS shows the actual lab testing setup. You can see compression testing machine. Cylindrical cube specimens are performing testing. THIS is a real-life testing environment. ENGINER's note explanation. The engineer's note says, ACCURATE laboratory testing is necessary to accurately evaluate structural performance and durability. Meaning, TSTING decides whether the design is successful or not. REAL understanding. Now understand it in a simple way. If testing will not take place, design will remain theoretical only. If the test is not successful, wrong data will be received. Wrong conclusions will be drawn. But if the testing is accurate, the correct comparison would be. The best mix will be identified. If you've learned this far and found this content useful, so subscribe to the channel now and press the bell icon, so that the upcoming advanced civil engineering topics are not missed. Final takeaway. Laboratory testing validation stage. COMPRESSIV strength core parameter. DNSITY packing quality indicator. Bonding wrap concrete as biggest challenge. Compressive strength test. Now let us focus on the most important parameter of concrete testing. COMPRESSIV strength test. WHAT is compressive strength. First, let's understand the basics. COMPRESSIV strength means of a concrete specimen to resist compressive load. Simple language. HOW much load can the concrete bear without breaking. This property decides, is the structure safe or not? What is the load-bearing capacity? Why this test is important? Now comes the question. Why is this the most important among so many tests? Because concrete structures work mainly in compression, such as columns, footings, slabs. If the compressive strength is low, so the entire structure may be unsafe. So this test core performance indicator. STEP testing process. Now let's understand how the test actually performs. Step 8 Specimen placement. The concrete cube specimen is placed in a compression testing machine. Points to note. Must be perfectly aligned. Load evenly. If the alignment is wrong, the result will also be wrong. Step 2 Load application. Now what the machine does is APPLIES load gradually. THIS load is not given suddenly. Rather it is increased at a controlled rate. Why? So that actual behavior can be observed. Step 10 Failure point. Comes a point. WHERE the specimen cracks and fails. THIS is the critical moment. Step 4 Strength calculation. Maximum load at which the specimen failed. Based on the same COMPRESSIV strength calculation is performed. Conceptually, the formula STRENGTH load bata area. Right side image explanation. Image you see now is THIS is the actual compression testing machine. In this, cube specimen is kept. Load is being applied from above. Cracking will gradually develop. THIS is the moment where concrete reaches its limit. BHAVIOR of wrap-based concrete. Now the most important part. RAP concrete behave in this test. According to research, SHOW is lower compressive strength. Why? AGED bitumen coating is applied on the aggregates. This coating reduces bonding, disturbs load transfer. HENCE failure happens quickly. FAILURE pattern understanding. Now let's understand a little deeper. In normal concrete, is uniform and controlled. But in wrap concrete, CRACKs develop quickly. FAILURE is irregular due to weak bonding. THIS directly indicates weakness of its interfacial transition zone. The engineer's note says, COMPRESSIV strength key indicator of structural performance. Meaning, if the strength is good, so the material is reliable. If the strength is low, so improvement is needed. PRACTICAL insight. Now understand from field perspective. JUST designing a mix is not enough. ACTUAL performance testing is essential. SEVERAL times a theoretically good mix practically fails. THATSY engineers always depend on lab results. FINAL takeaway. COMPRESSIV strength most important concrete property. IT decides the safety of the structure. STRENGTH reduction is common in wrap concrete. BONDING weakness is the main reason for this. So friends, so far in this entire lecture, we have prepared a very strong engineering foundation for this research topic. And as you can see on this screen, have explained all those important concepts in step-by-step detail in part 1 of this entire topic. Were very important to understand the actual engineering results that would come later. Because any engineering research cannot be understood directly from the results. Before that, it is important to understand its foundation, problem, science and methodology. And this is the entire journey we have understood together so far. If we quickly recap the entire learning of part 1. So first we figured out wrap foundation. Meaning what actually is reclaimed asphalt pavement, i.e. wrap material. It obtained from existing asphalt roads. Why is it recycled? And what is the complete process of collection and processing? We also understood that recycling is not just a cost reduction method in modern highway engineering. Rather, it has become a major requirement for sustainable infrastructure development. Because wrap material reduces construction waste, conserves natural resources, and supports environmentally responsible construction. After this, we understood the biggest engineering challenge of this entire research. Engineering problem. where we saw in detail that RAP aggregates do not behave like normal aggregates. Why? Because aged bitumen coating is present on their surface. And this coating creates a challenge in forming proper bonding between the cement paste and the aggregate, because of which interfacial bonding may weaken. Its interfacial transition zone may weaken. Internal strength may be affected and overall durability may also reduce. Meaning the problem was clear. But engineering is not limited to just identifying problems. Engineering also finds solutions. Important scientific concept of this entire research in detail. Science of solution, where we explained step by step. Article packing theory. Importance of packing density CPM, i.e. compressible packing model. And Taguchi optimization method. We understood that if aggregates are arranged scientifically in such a way that internal voids should be minimum, packing density should be maximum, particles should interact better, so can the bonding and performance of RAP concrete be improved? Can strength be better? And can durability be improved? To practically prove this concept, researchers followed a complete scientific methodology. Testing validation, where we understood in detail how was the material selection done, how was the RAP aggregates characterized, how was the experimental mix design prepared, how were concrete specimens prepared, how was the laboratory testing performed, how was the compressive strength evaluated, and behavior up to the microstructure level, how to analyze to be done. Meaning, if we say in simple language. So in part 1 we covered this entire research topic. Understood. The foundation understood. The engineering problem understood. The science of solution, and also understood the complete methodology in detail. But friends, now the biggest engineering question arises here. And perhaps the same question might be running in your mind right now. I understood the theory. But does this optimization actually work in practical life? Does particle packing really improve the strength of RAP concrete? Is durability really better? Does bonding improve? Or else, do limitations still persist? And friends, interesting, practical and result-oriented phase of this entire research begins. That means part 2 is coming next. As you can see on the screen below. We will understand in detail in the next part. Strength comparison, durability performance, practical applications, real engineering limitations, and most important, what do the final engineering results say? Meaning, so far we have understood the science and methodology. But in the next part, we will see actual engineering results. So stay connected with civil engineering infrastructure. Because in the next part we will see how successful this entire research actually proved to be in practical reality. So friends, have reached the last and most important stage of this entire research journey, where we started with a theoretical concept. And moving forward step by step, we have reached engineering reality. And as you can see on this screen, this entire research represents a complete engineering journey. From theory to engineering reality. Meaning, how a simple research idea is converted into practical engineering understanding. And then reaches real-world infrastructure solutions. If we look at this entire journey from an engineering perspective, So first we figured out wrap material, meaning what is reclaimed asphalt pavement, i.e. wrap. It obtained from existing asphalt pavement, how it is recycled, and how important is its role in sustainable construction. After this we understood engineering problem, where we observed that due to aged bitumen coating on the surface of wrap aggregates, between the cement paste and the aggregate may be weak, because of which weak its may develop, internal voids may increase, strength may decrease, and durability may also be affected. But the purpose of engineering problems is not just to point out the problem. Solution also has to be found. And that is why we understood in detail particle packing science, where we saw that if aggregates are scientifically optimized, and the particles should be arranged such that internal voids should be reduced, packing density should be increased, better particle contact should be developed, so the overall performance of concrete can be improved. Also understood the scientific approaches for this. CPM, i.e. compressible packing model, Taguchi optimization method, mixed design optimization. After this the researchers validated the theory at the practical level. Laboratory testing, where concrete specimens were prepared, compressive strength tests were performed, density evaluation was done, bonding behavior analysis done, and the microstructure was studied. And then we arrive at on-result analysis phase, where actual engineering findings came to light. Research has shown that better particle packing can reduce internal voids, strength and durability can be improved, sustainable construction potential can be increased. But engineering reality also showed that some limitations also exist in wrap concrete, because challenges like bonding issues and its weakness still remain important considerations. Meaning, this is not a magical solution. But if correct mixed design, proper optimization, and scientific methodology is followed, so wrap-based concrete can become a strong alternative for future sustainable infrastructure. And friends, if we understand the biggest takeaway from all this research, so that is that engineering is not just about using materials. Engineering is about understanding the correct problem, develop a scientific solution to do, and it is called validating it in practical reality. And this is what this entire study has taught us. That future infrastructure will not only be stronger, rather it will also be smarter, sustainable and resource efficient. And in this direction, wrap recycling technology can play a very promising role. But friends, now the biggest question is, did optimized particle packing actually prove successful at the practical engineering level? Has the strength of wrap concrete really improved? Did durability performance actually improve? WHAT do the actual results of laboratory testing say? And what was the final engineering conclusion of the researchers? We will understand the answers to all these important engineering questions in detail in the next part though, where we will see actual strength comparison, durability performance results, practical applications of wrap concrete, real engineering limitations, and final research findings. Meaning, this is not a magical solution. But if correct mixed design, proper optimization, and scientific methodology is followed, so wrap-based concrete can become a strong alternative for future sustainable infrastructure. And friends, if we understand the biggest takeaway from all this research, so that is that engineering is not just about using materials. Engineering is about understanding the correct problem, develop a scientific solution to do, and it is called validating it in practical reality. And this is what this entire study has taught us. That future infrastructure will not only be stronger, rather it will also be smarter, sustainable and resource efficient. And in this direction, wrap recycling technology can play a very promising role. But friends, now the biggest question is, did optimized particle packing actually prove successful at the practical engineering level? Has the strength of wrap concrete really improved? Did durability performance actually improve? WH80 do the actual results of laboratory testing say? And what was the final engineering conclusion of the researchers? We will understand the answers to all these important engineering questions in detail in the next part though, where we will see actual strength comparison, durability performance results, practical applications of wrap concrete, real engineering limitations, and final research findings. Meaning, so far we have understood the science and methodology. But in the next part, we are going to see actual engineering reality. So don't miss the next video, because that's where you'll find out how successful the theory actually proved to be in practical reality. Have seen this entire learning journey complete till here? Are really a serious engineering learner? Found this entire content valuable? So definitely support civil engineering infrastructure. Subscribe to the channel, press the bell icon, like the video, and do share it with your civil engineering friends. I am Rahul Pandey from Civil Engineering Infrastructure. We will meet again in the next practical engineering lecture. Till then, keep learning, keep understanding, and keep exploring engineering in a practical way. Thank you.